Hey everyone, my name is Kevin Tren, and I'm a PhD student at ASUCC. My advisor is Dr. Joe O'Rourke, and I also work closely with Dr. Carver Beerson. Today, I'll be making a case for why Europa's metallic core may have formed later than we typically assume. Before getting into my research, I want to spend some time covering background. First, I'll talk about Europa's current internal structure and why we believe Europa has a metallic core today. Next, I'll talk about things related to Europa's formation and heat budget. Then I'll talk about my preliminary results and end with the model that I am currently developing. First, I'll start with a simple but important question. What is Europa's current structure? Currently, our community believes that Europa is differentiated into a metallic core, silicate mantle, ocean, and ice shell. We have poor constraints on the size and composition of this iron-rich core. Our current models are constrained by gravity data. The distribution of mass inside of a planet is directly responsible for the gravity field that it produces. In the 1990s, the Galileo spacecraft visited Europa and returned gravity data. From that, we can calculate the bulk density and moment of inertia factor, or MOI, of a moon, where MOI is a single number that describes plausible mass distributions of a planetary body. Together, these two values provide non-unique constraints on Europa's internal structure. Currently, it's not yet necessary to invoke a metallic core with the information I brought up so far. Bulk density and MOI constraints can lead to a two-layer moon that has a hydrosphere and a rock metal interior. However, we run into some problems if we do that. This was done in a study by Anderson and colleagues in 1998. In a two-layer model, we get a relatively high density for the rock metal interior of at least 3,800 kilograms per cubic meter. This is unlikely because we expect the bulk density of the rock metal interiors of the Galilean moons to not increase as we get farther away from Jupiter. On the right, we have Io, which is slightly bigger and closer to Jupiter. Its bulk density is much less, about 3,500 kilograms per cubic meter. So, based on bulk density, MOI, and comparison of the Galilean moons, we dismiss the two-layer model of Europa in favor of a three-layer model, and say that Europa probably has a metallic core. Recapping internal structure, we use gravity data to support the existence of a metallic core in Europa. Now to our next question. What controls Europa's heat budget? For large rocky planets like Earth, core formation begins during the accretion process. This is because there is enough accretional heat to raise temperatures up to the melting point of metal or silicates. On the other hand, smaller bodies like Europa are too small to form a metallic core during accretion. There is not enough mass. Instead, Europa's core formation was triggered later primarily by radiogenic heating. Tidal heat is mostly dissipated in the ice shell and thus strongly affects ocean thickness. But the evolution of the rock mount interior is independent of ocean thickness, so we can ignore tidal heating when investigating core formation. The amount of radiogenic heat available depends on the formation time of Europa. This happens in early solar system history. And anytime we talk about events in the early solar system, it's important that we define calcium aluminum rich inclusions, or CAIs, which are the first solids to form in our solar system. I will be using CAIs as a time reference. The core of Jupiter formed within 1 million years after CAIs. This proto-Jupiter possessed an accretion disk for the next 3 to 4 million years where moons could form. Using this timeline, we bound the formation time of Europa to be 3 to 5 million years after CAIs. Europa's formation time is important because of a particular radioactive isotope, aluminum-26, which is very powerful and short-lived. Here is a table of long and short-lived isotopes that I used. The top 4 rows are long-lived isotopes. The bottom 3 rows are short-lived isotopes. Already, we can see that aluminum-26 produces an insane amount of heat compared to the other isotopes by orders of magnitude. Also, the half-life of aluminum-26 is only about 700,000 years. Just by viewing the formation time from 3 to 5 million years, we span about 3 half-lives of aluminum-26. This means that formation time of Europa itself determines how much aluminum-26 was accreted onto Europa. If Europa formed early, then there is a lot of aluminum-26, and we get a warm thermal history. On the other hand, if Europa formed late, that most of the aluminum-26 will have decayed before being accreted onto Europa, so we get a cooler thermal history. Therefore, formation time indirectly determines the amount of heat available for Europa. Now we're ready to tackle the big question. How early could metallic core formation begin in Europa? This is an important question because current studies typically make assumptions about Europa's thermal history that are worth revisiting. One assumption is that Europa dehydrated all of its silicates shortly after accretion. The other assumption is that the metal core forms shortly after dehydration. Both of these assumptions may lead to artificially warm thermal histories. In my work, I explore the effects of hydrated silicates on the timing of Europa's metallic core formation. As I investigate this question, I would tend to make assumptions that favor early core formation, so my incoming results should be interpreted as early bounds. I'm going to show that, despite these assumptions, core formation in Europa still happens pretty late. I use an energetics approach. After accretional heat has been spent on establishing Europa's initial conditions, we can write an energy balance for Europa's thermal evolution. On the left, we have our main source of heat production, and this energy gets spent on three other things: latent heat, secular warming, and heat loss to the ice shell. However, computing loss to the ice shell is complicated. My preliminary work will prioritize calculating lower bounds on how long it takes to initiate core formation by assuming that no heat is lost to the shell. Including this term will only strengthen my argument that core formation in Europa can be delayed. Latent heat can be separated into two more processes: silicate dehydration and core formation. Whenever we are spending energy on latent heat, we are changing the phase of a material without increasing its temperature. It's also important to know when metal starts melting in Europa's interior, because once that happens, core formation may begin. For moons like Europa, we assume an iron-rich core with some unknown amount of sulfur. Conveniently, a study was done on Ganymede's core, and they created this nice figure of the iron-sulfur system. The x-axis represents weight percent sulfur in the core, and the y-axis is temperature in Kelvin. The top and bottom lines represent the liquidus and the solidus. The solid and dashed lines represent different pressures. Let's focus on this dashed line, since the peak pressure of Europa is close to 5 gigapascals. The melting temperature is highest for pure iron at around 1950 Kelvin. As you increase the sulfur content, the melting temperature decreases all the way to a minimum of 1250 Kelvin. This minimum is called the eutectic. An iron core containing the eutectic amount of sulfur corresponds to the earliest core formation possible. Now that we know the range of temperatures that can initiate core formation, we can plot the early bounds of when core formation may begin. The x-axis is Europa's formation time after CAIs, and the y-axis is the time after Europa's birth. The dashed black line is when Europa finished dehydrating all its silicates. From blue to red, each line represents the time when metal melting can start. Blue is sulfur-rich, red is sulfur-depleted. Immediately, we see a couple interesting things. One is that sulfur-poor core compositions are not guaranteed to form, whereas sulfur-rich core compositions are easier for Europa's energy budget. On top of that, we believe that Europa and the other Galilean moons formed closer to 5 million years after CAIs, so this also favors more sulfur-rich core compositions. While Jupiter possessed an accretion disk for 3 to 4 million years, it continuously formed moons in its disk that migrated inward and eventually got consumed by the planet. The Galilean moons we see today are believed to be the last surviving generation of Jupiter's large moons. This theory also supports the requirement for sulfur in the metallic core. The other cool finding is that core formation could be delayed by at least billions of years. Look at the earliest expected case, a eutectic core composition and formation time of 3 million years. Core formation begins at around 1.3 billion years after formation, which is still very late. Again, what I've shown so far are preliminary calculations. Currently, I'm developing a 1D radiothermal evolution model, which will yield more detailed and robust results. Here's an example plot of what I implemented so far. Although there are so many items on my to-do list, we can already gain some rough insight. The x-axis is time after accretion, and the y-axis is radial distance from Europa's center. The dashed black lines are temperature contours in Kelvin, and the red lines mark the times when we first reach a temperature when a new geologic process could begin. Once each process has been implemented, the remaining red lines will shift later in time, possibly to the point where core formation and volcanism never occur. I also include the ocean boundaries for now, but again, I don't include tidal heating or ice shelf convection, so I wouldn't use my model to predict ocean thickness. What you see here is just an artifact of a heat fluxes from the deep interior into the ocean. This model is useful for the evolution of the rock metal interior. Now we have two plots where the only difference between the left and right plot is the formation time of Europa. The left plot is an early formation case, which means there's a lot of aluminum-26 available for heating, so we reach much higher peak temperatures than the plot on the right, which represents a late formation case. Again, this demonstrates the importance of Europa's formation time in its evolution, because that affects the abundance of radioactive isotopes available for heating. We also see that the metallic core formation can happen pretty late, and that point will be further strengthened as I include other processes on my model checklist. Again, this is very much in the works, so I'll leave further discussion on this model once I make more coding progress. For now, I want to wrap up my talk with my take-home message. From an energetic standpoint, it is hard to form a metallic core in Europa. Lots of radiogenic heat is consumed by silicate dehydration and core formation. In fact, energetics doesn't guarantee that Europa will form a core. We're working with a pretty small heat budget, but if Europa does have enough energy to form a core, then Europa's metallic core formation may have started billions of years after accretion. This slide is purely for networking. Again, my name is Kevin Trin. I am a second-year PhD student at ASU/CC, and I'm interested in studying how planetary formation and evolution affects the potential for life in icy moons. You can contact me via email or Twitter, and if you're interested in STEAM outreach, I am happy to look for volunteers to speak about their science to a broad audience in plain speak using visual slideshows and Instagram. If you have questions about my science, or if you're interested in learning more about this outreach opportunity, please reach out to me and I'd be very happy to get back to you. Thank you.